Let's now solve some exercises and then we can move on to the next chapter in the next week. So let's start with this second one where we have to solve the following differential equation, which is 2x plus tan y times dx plus x minus x squared tan y times dy equals 0 by first finding an integrating factor. We start the solution by naming these parts m and n respectively. This is what we always do. So m is 2x plus tan y and n is x minus x squared times tan y. And then we calculate these partial derivatives, del m del y and del m del x. What will you get if you differentiate this partially with respect to y? 2x contributes 0 because it's constant then, and differentiating tan y you get secant squared y. And then you differentiate this one partially with respect to x. So that will give you 1 minus 2x tan y. And then we calculate this quantity, say 1 over m times del n del x minus del m del y. By looking at these partial derivatives, you can clearly see that this is not an exact equation. So we just use the values here. So we do not write what m is here. There is no point to keep writing that. So we just keep it as m. We know what it is, so we will use it when we need it. What is this difference? Del n del x is 1 minus 2x tan y, and del m del y is secant squared y, so minus secant squared y. 1 minus secant squared y is minus tan squared y, and then you can take minus tan y common out. So that way the other factor becomes tan y plus 2x. Now you see what m is, that is just this 2x plus tan y. So after cancelling these two things you get minus tan y. So that means this quantity is a function of y only, and in this situation we know what to do to find an integrating factor. So an integrating factor, which say we are calling it if, is this, the exponent of integral of minus tan y with respect to y, of course, which if you do, I am not going into the details, you already know these things from calculus. You are going to get cos y, so that is your integrating factor. Now we have to multiply the original equation on both sides by cos y, and that will turn the equation into another equation, equivalent equation, which will be exact, and then we can solve that. So we write accordingly, multiplying the given t means differential equation by cos y, we get this. You go back to the original equation, you do the multiplication yourself, you see that this is what you get. 2x cos y plus sin y times dx plus x cos y minus x squared times sin y dy equal to 0. And here also, actually this is exact. Although you need not check, well, if you want you can check. You differentiate this partially with respect to y and this one partially with respect to x, you will see that you are getting the same thing. Because we have already called those functions m and n, so let's give them some new names, m1 and n1. So we know that this is exact. So we now are going to go through the procedure for solving this equation. Hence we next write like this, since the above equation is exact, above equation means this one, there exists the function capital F such that del f del x is m1 and del f del y is n1. So next, according to the procedure, you integrate this first equation between these two equations, you integrate this one partially with respect to x. So that way the left hand side will be f, and if you integrate the right hand side, y is constant because we are integrating with respect to x. So x gives you x squared divided by 2, but already there is a 2, so you are getting x squared cos y. Similarly, this sin y term, which is constant, gives you x sin y. plus phi of y, where phi is an arbitrary function of y. Now next we use this expression along with this one to find phi of y. How? Well, you first note that this is equal to del f del y, alright. But now that you have found something about f, namely that f is this, which you haven't really found totally because this part is still unknown, but still you have found something. So using this expression you can calculate del f del y. So you differentiate the right hand side partially with respect to y. So then x is constant. So this cos y will become minus sin y. So that way you are getting minus x squared sin y. And this term will give you what? If you differentiate sin y, you are going to get cos y. X stays constant. So that way you are getting x cos y. Plus, when you differentiate this partially with respect to y, that turns into ordinary derivative. Differentiation with respect to y, because this is the function of y only. So you get the ordinary derivative of phi with respect to y, phi prime of y. And now you can clearly see that these two terms cancel from both sides and these two also cancel from both sides. So we are getting this then, that phi prime of y is equal to 0 because everything else is just vanishing. From which actually, this does not really imply that phi of y is 0, but more generally it implies that phi of y is constant, some constant, any constant. However, we have chosen phi of y to be 0. Why? Why are we not using phi of y equal to c here? That is because we are going to use that value here. And when after putting that value, we write the general solution. General solution means the solution to the modified equation. That solution is f equal to constant. So if you have another plus constant here, those two constants can be merged together to form just one constant. So we do not gain or lose anything by just simply taking phi of y equal to 0. If anything, it simplifies the situation. That's it. So that way, this is our f, x squared cos y plus x sin y. And so this is the one parameter family of solutions to what? To the modified equation, the exact equation. And it turns out that this is also a one parameter family of solutions to the original equation. You think for yourself why. Let's consider another one, number 6, where this is the differential equation 8x squared times y cube minus 2y to the power 4 dx plus 5x cube y squared minus 8x y cube dy equal to 0. We have to find an integrating factor of this specific form, x to the power p times y to the power q, and then solve the equation. So it's not going to follow any procedure that we have seen already. We just have to work with this information that there exists an integrating factor of this form and find one, and then we can multiply the equation by the integrating factor and then we can solve it. Let's not write sentences in the solution and let's see the actual calculation. You can write the entire solution formally yourself. So what is it that we want? We want to find an integrating factor of this form. So what can we possibly do at this point? At this point we can possibly only do this. We multiply this equation by this itself, turning it into this other equivalent equation. If this is to be an integrating factor, then this modified equation needs to be exact. So we can apply the condition for exactness on this equation, and that way maybe we can find this p and q. So let's first see what we have got here. If we really do the multiplication, the corresponding exponents get the plus p and plus q. So here you have p plus 2, q plus 3, okay. Here you will just have p because originally there was no x, and here you will have q plus 4. P plus 3, q plus 2, there we have p plus 2 and q plus 3, okay. and here it will be p plus 1 because here we have x to the power 1 and q plus 3. So next we name these things as usual m and n, and then this is the condition for exactness. Del m del y should be equal to del n del x. So now we carefully calculate these partial derivatives and let's see what we have got. This is what we have got. So we are differentiating n with respect to y partially, so x will be constant. So from this first term we are going to get 8 times q plus 3 times x to the power p plus 2 times y to the power q plus 2. The exponent gets reduced by 1, the usual power rule, minus 2 times, so this part stays because we are differentiating with respect to y, times q plus 4 times y to the power q plus 3. Alright, and now this one partially with respect to x, so now y is constant, so this one will be 5 times p plus 3 times x to the power p plus 2 times y to the power q plus 2 minus 8 times p plus 1 times x to the power p times y to the power q plus 3. Now it looks quite scary, no? I mean, what is it that you have to find from here? P and q. But if you look carefully, very nicely we have got the same things on both sides. Almost the same. X to the power p plus 2 times y to the power q plus 2. On this side also we have this. But the coefficients apparently look different. Same with these two things. So you instantly realize that it will be just enough to equate the corresponding coefficients on both sides. That way we will get two equations involving p and q, and then we can solve them. So here you have to write one sentence before you write these two equations. Equating the coefficients of this and this on both sides of the above equation, we get the following. 8 times q plus 3 should be equal to 5 times p plus 3, and minus 2 times q plus 4 should be equal to minus 8 times p plus 1. There is a high chance of making a small mistake here. That mistake actually won't affect anything mathematically, but say you say that you are equating coefficients of x to the power p times y to the power q plus 3 on both sides, and you do not write these minuses. The minuses are also parts of the coefficients. So although they will ultimately get cancelled, but ideally they should be written. Otherwise it might look like you don't really know what you are doing. And then simplifying these equations a little bit, you get these two. 8q minus 5p equals minus 9 and q equals 4p, which if you solve, you get these values. P is minus 1 over 3 and q is minus 4 over 3. So this is an integrating factor. And now you go back and multiply the original equation by this, or you can just simply substitute these values in that already multiplied modified equation. That equation will be exact. You solve it, find a one parameter family of solutions, and that's it. That part I am leaving to you. Let's see another one, number 10 say, where we have to solve this differential equation 10x minus 4y plus 12 times dx minus x plus 5y plus 3 times dy equals 0 by making a suitable transformation. This is a known type, and this follows that thing that we saw in the previous video. So as per the procedure, we first identify these quantities, these coefficients a1, b1, a2 and b2. a1 is 10, b1 is minus 4, a2 is minus 1. Do not forget this minus, okay. If you are prone to making this mistake, you can write one more line, writing the equation as this plus minus x minus 5y, that you do that, okay. But anyway, a2 is minus 1 and b2 is minus 5. So now we calculate a2 divided by a1, which you can clearly see is minus 1 divided by 10. Okay, so minus 1 over 10. And b2 divided by b1 is minus 5 divided by minus 4 or 5 over 4. They are not equal. So that means we know what we want to do next, which is we consider this system obtained by equating these parts to 0. This equals 0 and this equals 0, and then we solve the system. So you can go through the solution process and you will get this solution. I have written the solution in this form. It just means that x is minus 4 over 3 and y is minus 1 over 3. And that just means that this is the transformation we have to use to transform the original equation into another one, where the new variables are capital X and capital Y. And you get this transformation using these solution values. Original variable equals new variable plus this, that means minus 4 over 3. Similarly, this one for Y. So you substitute these things back to the original equation and you run the process. Because we have already gone through one example of this in the previous video, if you remember. So I am leaving this part to you. What will it get you? It will transform the original equation into another equation, which this time won't be exact, but it will be what? Homogeneous. And then you can solve that with a further transformation that you already know how to do. I mean, in the homogeneous equation, the new variables are x and y. So you then use the transformation y equals vx, capital Y equals v capital X. That will then turn the homogeneous equation further into a separable equation, which you solve, and then you bring the original x and y back. You have to go through two reverse transformations. And let me end the video here itself. There are other exercises in this set. You go through them and try to solve them, as many as you can. But if you find any difficulty, you write in the comment section below, specifically saying which ones you want me to solve. So next week we are going to start the next chapter, where we will see how we can use these methods that we have learned in this chapter to solve some problems which arise in other disciplines outside of mathematics.